Halo, Assalamualaikum.
Waalaikumsalam, Pak.
Sudah siap semua kah? Gimana Mbak Ramadiana, sudah siap? Mas saya sudah gabung? Ya, ya bagus Mas. Untuk foto Mas, itu kalau bisa foto-foto teman-teman panitia yang kurang formal, itu ini Mas, dipasangin foto dan dimasukkan foto-foto yang agak ini Mas, ya diganti yang agak formal kalau bisa, misalnya yang ya nanti silakanlah disesuaikan ya. Karena ini kan meetingnya nasional dan membawa nama UNDIP. Halo Mas Ayas.
Ya Pak, baik Pak.
Ya gitu ya, jadi foto-foto seperti foto yang apa namanya untuk pribadi-pribadi gitu ya, itu diganti dengan foto-foto yang formal ya. Jadi biar kelihatan, terutama panitia. Kalau yang peserta kita kan nggak bisa ngatur ya. Nanti takutnya ada teman-teman yang lupa gitu kan.
Baik Pak ya.
Ya. Prof Suci sudah oke. Baru saya dia telepon balik karena biasa dia kalau udah last minute on schedule baru dia telepon Mas. Dia sudah ready Mas. Nanti materinya tentang kriging ya. Materinya tentang geostatistik dia Mas. Mas, ini tanggalnya ini apa enggak 2 ya Mas? 13 sampai, kalau judulnya workshop dan webinar, berarti tanggalnya sampai hari Minggu Mas. Ya enggak? Ya, tanggalnya itu Mas ya. Jadi 13 sampai berapa itu? 15 ya, November 2020. Ya, terus saya lihat tulisan 13 sama 15 itu enggak ini Mas, enggak connect sama tulisan di atasnya. Bisa enggak itu ya dimiripin dikit. Kelihatan dia lain gitu. Ini apa nih? Slide-nya gambar ya? JPEG.
Iya Pak, PowerPoint JPEG Pak.
Oh, kalau dia bukan PowerPoint bisa di ini, dia bisa di apa namanya, bisa di copy. Ya. tapi nggak apa-apa Mas. Coba cari mirip yang agak mirip dikit gitu. Ya, kasih tanggalnya 13 sampai 15 November ya. Nanti direkam di YouTube ya Mas. Direkam.
Sudah Pak, sudah live streaming Pak.
Oh, oke. Maksud saya nanti di videonya di-upload di YouTube. Kalau di-upload Mas, itu ini Mas, nanti mereka bisa bertanya pada hari yang Senin ya. Mereka bisa bertanya waktu Suci ngasih video, terus kemudian nanti pertanyaannya itu akan dilihat, tapi tidak dijawab ya. Nanti Suci akan menjawab, dia akan lihat videonya di YouTube, kemudian dia akan menjawab lewat teks nanti Mas, ya, lewat tulisan. Nanti tulisan itu disampaikan di apa namanya websitenya Register, ya, di acara ini, ya. Jadi kalau ada yang mau lihat jawab pertanyaannya siapa, jawabannya siapa gitu. Nanti ada di situ. Ya, dia akan kirim itu, Mas.
Baik Pak.
Ya. Itu kalau kamu on suaranya berisik ya, Mas? Ya. Ya. Coba Mas di on, Mas.
Sudah di unmute Pak. Oh berisik backsound ya Pak ya? Noise ya Pak?
Iya. Iya, coba kamu ini kan kamu on nih suaranya.
Oh, iya.
Nah, itu dia, Mas. Nah, kedengeran nggak, Mas? Itu suara apa itu, Mas ya? Mute punyamu, Mas. Coba di unmute, Mas. Mas Ayas. Iya. Terus ya coba ini Mas, kamu bicara coba Mas.
Yes. Halo Pak.
Ya. Ya, nah, ini bersih nih Mas.
Oh, iya.
Ini bersih. Kalau tadi ada suara apa itu ya?
Oh iya Pak, itu cooler Pak.
Hah?
Selamat pagi Pak
Oh,
Helmi.
G.
Assalamualaikum.
G. Selamat pagi Pak Agus. G. Matur nuwun Pak Agus atas bantuannya Pak Agus.
Suaranya jelas Pak Helmi?
Keras suaranya bagus Pak Agus.
Oke, terima kasih.
G. Matur nuwun loh Pak.
Kami wah luar
Ya.
biasa Pak Helmi. Ya, selamat pokoknya semangat
Ya.
terus.
Selamat register Pak Agus.
Ya, selamat
Mudah-mudahan
Pak Helmi.
ya. G. Mudah-mudahan biar unit kegiatan mahasiswa ini berkembang ini Pak Gus.
Oh iya. Ini,
Nah, ini
yang ketua registernya siapa ini?
Ini Mas Ayas Pak Gus.
Mas
Mas
Ayas.
Ayas.
Oh,
Ya.
Ayas ya. Yang sudah daftar itu kemarin ya Ayas ya.
G, ya.
Yang daftar apa jadi apa? Volunteer untuk ini. Ayas. Mama Ayas. Volunteer untuk perubahan sikap.
Iya Pak, siap.
Ya. Ini tentang apa Pak Helmi? Pemetaan ROP ya?
Ini di depan tuh ada judul Pak di screen-nya Bapak.
Oh gitu.
Perubahan iklim dan pesisir.
Oh.
Perubahan iklim dan pesisir.
Oke ya.
Bahan-bahannya udah dikasih ya Mas Mas Ayas ke Pak Agus.
Sudah Pak.
Iya,
sudah.
ya. Sudah ya Pak Agus. Untuk sambutan pendek Pak Agus ya.
Ya, ya.
Oke.
Webinar. Bahan iklim.
Mas Ayas nanti ada sesi foto bersama Mas.
Ada Pak.
Ada, itu di depan apa di belakang?
Di belakang Pak. Setelah
Di belakang.
Tapi nanti bisa dimajuin Pak ketika sambutan-sambutan udah selesai dan sebelum masuk materi.
Iya. Ya, G. Ya, monggo Mas. Itu suara coolernya Ayas ya?
Sudah tidak, Pak.
Nah, itu udah hilang tuh. Dari mana ya Mas suaranya Mas? Nah, ini bersih suaranya Mas.
Iya, Pak. Sudah saya mute, Pak.
Wah, ini lagi dia Mas, desis dia Mas. Iya, ya, nggak apa-apa Mas, nanti bisa diatur Mas. Di PUI juga gitu dia Mas. Jadi kalau di PUI hidup itunya unmute gitu, suaranya kelihatan dengung. Saya nggak tahu juga itu apa penyebabnya ya. Kita mulai 8 berapa Mas? 8.30 apa jam ini Mas?
Jam 8:05, Pak. Sebentar lagi, Pak.
Oke, ya. Tanggalnya Mas, DC segera ya Mas. Jangan ke sini.
Bismillahirrahmanirrahim. Sebelumnya apakah suara saya terdengar?
Terdengar Mbak, sangat jelas.
Ya. Assalamualaikum warahmatullahi wabarakatuh. Saya Tiara Anggita, di sini selaku korlap acara workshop ReGISFest 3.0. Sehubungan dengan waktu yang sudah menunjukkan pukul 8.06, maka dari itu langsung saja kita mulai acara ini. Waktu dan layar saya berikan kepada MC.
Baik, terima kasih korlap. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semua. Selamat datang di acara Workshop Nasional ReGISFest tahun 2020. Yang terhormat, Wakil Dekan Bidang Akademik Fakultas Perikanan dan Ilmu Kelautan Universitas Diponegoro, Bapak Agus Trianto, ST MSc PhD. Yang kami hormati, Pembina UKM-F REGISTER Universitas Diponegoro, Dr. Muhammad Helmi, S.Si, M.Si. Yang kami hormati, moderator dan narasumber pada acara hari ini, serta seluruh tamu undangan dan peserta workshop nasional ReGISFest tahun 2020, baik melalui Zoom dan YouTube. Pertama-tama, marilah kita panjatkan puji syukur kehadirat Allah Subhanahu wa Ta'ala, Tuhan yang Maha Esa, atas kehendaknya kita semua dalam keadaan sehat dan dapat mengikuti acara Workshop Nasional ReGISFest 2020. Perkenalkan, saya Rahmadiana Dini selaku Master of Ceremony pada acara hari ini. Pada acara hari ini, Jumat 13 November 2020 sampai Minggu 15 November 2020, UKM-F REGISTER, PUI-PT-PKMBRP CoREM, dan Center of IZCM mempersembahkan workshop dan webinar nasional yang merupakan kegiatan World Class Professor Scheme B dalam rangka memeriahkan Hari GIS Internasional 2020. Acara ini bertemakan dampak perubahan iklim terhadap lingkungan pesisir. Sebelum dimulainya acara, marilah kita berdoa menurut agama dan kepercayaan masing-masing. Berdoa dimulai. Berdoa dicukupkan. Selanjutnya, saya akan membacakan susunan acara workshop online dampak perubahan iklim terhadap lingkungan pesisir hari ke-1. Yang pertama, pembukaan dan menyanyikan lagu Indonesia Raya. Yang kedua, sambutan-sambutan. Yang ketiga, pelatihan pemetaan bencana pesisir oleh Prof. Sucharita Gopal dari Boston University dan Dr. Muhammad Helmi, S.Si, M.Si. Acara yang keempat, ISOMA. Yang kelima, pelatihan pemetaan laut oleh Dr. Bambang Sukresno dari BLOL KKP Bali. Acara yang terakhir, penutup dan briefing hari kedua. Berikut adalah statistik peserta workshop online dampak perubahan iklim terhadap lingkungan pesisir. Para peserta berasal dari luar UNDIP sebanyak 282 orang, dan dari UNDIP sebanyak 114 orang, di mana berasal dari berbagai instansi, yaitu perguruan tinggi, instansi pemerintah BUMN, instansi swasta, maupun sekolah SMA, SMP, dan sederajat. Berikut merupakan sebaran peserta workshop online ReGISFest 3.0. Klausul eksonerasi. Panitia dibebaskan dari segala tanggung jawab hukum atas segala akibat hukum yang terjadi akibat layanan virtual yang diberikan, serta peserta dianggap mengetahui dan menyetujui tanggung jawab pribadi segala akibat yang timbul atas pilihan layanan virtual yang disediakan panitia. Workshop ini direkam dan disiarkan langsung melalui channel official akun Register Undip melalui tautan YouTube berikut. Perkenankan saya selaku Master of Ceremony untuk membacakan tata tertib peserta workshop online dampak perubahan iklim terhadap lingkungan pesisir. Yang pertama, peserta wajib mengatur username Zoom meeting dengan format nama _instansi. Peserta wajib mengikuti rangkaian workshop dari awal hingga akhir acara. Peserta diharapkan menyalakan kamera, on-cam, dan diwajibkan mematikan suara saat acara berlangsung. Peserta diwajibkan menggunakan virtual background yang telah diberikan oleh panitia melalui email. Peserta dilarang keras mengganggu keberlangsungan acara. Jika dirasa mengganggu, maka akan ditindak tegas oleh Korlap berupa dikeluarkan dari Zoom. Peserta diwajibkan mendokumentasikan sebagai bukti hadir yang akan dimasukkan ke dalam formulir H sebagai presensi kehadiran. Peserta diwajibkan mengisi formulir H pada yang akan dibagikan oleh panitia saat acara berlangsung. Formulir H berisikan daftar hadir peserta, evaluasi kegiatan, bukti mengikuti kegiatan, dan bukti persyaratan. Yang terakhir, peserta akan mendapatkan modul dan data setelah berlangsungnya agenda kegiatan workshop selesai. Berikutnya sesi tanya-jawab. Sesi tanya-jawab dilakukan di akhir pada setiap sesinya setelah pemateri selesai melakukan pemaparan. Yang kedua, durasi sesi tanya-jawab akan berlangsung selama 30 menit. Yang ketiga, peserta yang mengikuti kegiatan melalui platform Zoom dapat memberikan pertanyaan dengan cara raise hand terlebih dahulu dan nantinya akan dipersilahkan oleh moderator untuk bertanya langsung kepada pemateri. Yang keempat, apabila peserta yang memiliki kendala untuk menyalakan suara, pertanyaan dapat disampaikan melalui kolom chat Zoom meeting. Yang kelima, peserta yang mengikuti kegiatan melalui live streaming YouTube dapat memberikan pertanyaan melalui form yang disebar oleh panitia saat pemateri melakukan pemaparan. Door prize workshop. Door prize workshop berupa 2 pieces personal use license ReGIS. Pemenang door prize workshop adalah peserta teraktif berdasarkan pertanyaan terbaik. Rincian distribusi door prize workshop sebagai berikut. Pemenang door prize workshop hari pertama 1 pieces, pemenang door prize workshop hari kedua 1 pieces. Pengumuman pemenang door prize workshop diumumkan pada saat acara seminar online Minggu 15 November 2020 pada sesi pengumuman pemenang door prize. Baiklah, untuk membuka acara pada hari ini, marilah kita membaca basmalah secara bersama-sama. Bismillahirrahmanirrahim.
Bismillahirrahmanirrahim.
Acara selanjutnya yaitu menyanyikan lagu Indonesia Raya. menuju acara yang kedua, yaitu penyampaian sambutan-sambutan. Sambutan pertama akan disampaikan oleh Ketua Pelaksana ReGISFest 2020, yaitu Saudari Mariam S. Taib. Kepada Saudari Mariam S. Taib, waktu dan layar saya persilakan.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, yang terhormat Bapak Dr. Agus Trianto, ST, MSc, PhD, selaku Wakil Dekan 1 FPK. Yang saya hormati Bapak Dr. Muhammad Helmi, S.Si, M.Si, selaku Ketua PUI CoREM, sekaligus pembina kami, pembina UKM-F REGISTER. Yang saya hormati para pembicara pada acara workshop kali ini, yaitu Profesor Sucharita Gopal, PhD dari Boston University, Dr. Bambang Sukresno, M.Si dari Balai Riset Observasi Laut. Tidak lupa juga pada para teman-teman panitia yang saya cintai dan saya banggakan. Pertama-tama, marilah kita panjatkan puji syukur kepada hadirat Allah Subhanahu wa Ta'ala yang telah melimpahkan rahmat-Nya dan karunia-Nya sehingga kita dapat berkumpul pada acara workshop ReGISFest pada hari ini dalam keadaan sehat walafiat. Salawat serta salam semoga terlimpahkan kepada baginda Nabi kita, Nabi besar Muhammad SAW, kepada keluarganya, sahabatnya, pengikutnya, dan kepada kita sekalian. Saya selaku ketua acara dari ReGISFest mengucapkan selamat datang kepada para peserta yang akan mengikuti kegiatan workshop pada hari ini. Saya mengucapkan terima kasih kepada para pihak yang telah terlibat pada acara hari ini, baik dari pihak universitas, pihak kampus FPIK, pihak PUI CoREM, dan pihak-pihak instansi yang terkait. Acara ReGISFest ini merupakan kepanjangan dari Remote Sensing and GIS Festival dalam rangka memperingati GIS Internasional. ReGISFest ini memiliki 2 sub acara, yaitu workshop dan webinar. ReGISFest ini juga telah terdaftar di GISD yang diselenggarakan oleh S.Si Internasional. Pada kegiatan workshop ini pastinya akan banyak materi yang mengenai RS dan GIS. Harapannya dapat tercipta forum diskusi yang dalamnya baik peserta dan panitia dapat belajar mengenai RS dan GIS. Tidak hanya pada saat acara berlangsung, namun juga pada ketika acara telah selesai dan dapat belajar dan berdiskusi bersama. Sekian dari saya. Wassalamualaikum lebih dan kurangnya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih kepada Saudari Mariam S. Taib atas sambutannya. Selanjutnya, sambutan yang akan disampaikan oleh pembina UKM-F REGISTER kepada Dr. Muhammad Helmi, S.Si, M.Si. Waktu dan layar saya persilakan.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Selamat pagi.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat sejahtera bagi kita semua. Yang saya hormati Bapak Agus Trianto selaku Wakil Dekan FPIK Fakultas Perikanan dan Ilmu Kelautan Universitas Diponegoro. Yang saya hormati narasumber di sini Profesor Dr. Sucharita Gopal from Boston University, USA, dan Dr. Bambang Sukresno, S.Si, M.Si, dari Balai Riset dan Observasi Laut, ya, Peranca, Bali, yang akan ikut memberikan sumbangsih materi dan pengalamannya terkait bidang remote sensing dan GIS pada workshop hari ini. Bapak, Ibu, dan saudara-saudara sekalian, marilah kita panjatkan puja-puji dan rasa syukur kita kehadirat Allah Subhanahu wa Ta'ala, ya, Tuhan yang Maha Kuasa, karena pada pagi hari yang berbahagia ini, pagi yang cerah ini di Indonesia, dan sore hari di Boston University. Jadi, good evening, Prof. Suci. Ya, thank you very much for your attention and your coming on this very valuable workshop that we have prepared together. Bapak, Ibu, dan saudara-saudara sekalian, kita memiliki 3 rangkaian acara ya. Hari pertama workshop dengan pemateri yang handal ya, dari Prof Suci. Beliau adalah ahli di bidang GIS dan juga sangat terkenal tidak hanya di kampusnya di Boston University tapi di kalangan peneliti di Amerika Serikat ya, khususnya bidang GIS. Alhamdulillah dengan kesibukan mereka yang beliau yang tinggi, beliau masih bisa menyempatkan untuk bisa hadir bertemu kita ya. Terima kasih juga ini kepada Pak Bambang ya, yang pengalaman beliau juga luar biasa ya, termasuk lulusan tercepat ya di program doktornya. Kemudian hasil risetnya juga sangat baik ya, dengan menggunakan data series yang panjang untuk pemodelan penginderaan jauh terkait dengan fishing ground. Nanti kita lihat seperti apa yang beliau sampaikan gitu ya. Kemudian dan bagaimana dampaknya terhadap perubahan iklim. Sebagai acara kedua besok itu materinya juga tidak kalah penting ya. Itu akan disampaikan oleh Kepala Pusat BMKG ya, Badan Meteorologi dan Geofisika Maritim Jakarta. Itu juga terkait dengan iklim, jadi sangat menarik dan bagus materinya ya untuk pembelajaran kita semua. Dan kemudian akan diberikan materi juga oleh Dr. Suharyanto. Pak Suharyanto ini adalah Direktur Tata Ruang Laut Kementerian Kelautan dan Perikanan Republik Indonesia. Jadi ini sangat luar biasa ya, artinya register bisa mengakses Pak Bambang ya, kemudian BMKG dan Kementerian Kelautan Perikanan ini ya, Pak Suharyanto, karena mereka juga punya jadwal yang sangat padat di kantornya. Selain itu juga mereka memberikan materi di berbagai perguruan tinggi ya. Kemudian di seminar itu kita juga mengangkat pakar untuk bisa memberikan materi yang lengkap ya. Kalau kita lihat, maaf yang tadi seminar itu materinya akan diberikan oleh Pak Suharyanto dari Kementerian Kelautan Perikanan ya, Direktur Tata Ruang Pesisir dan Laut, Kementerian Kelautan Perikanan Republik Indonesia, dan dari BMKG Maritim ya, itu yang seminar. Kemudian nanti Prof Suci akan memberikan materi juga pada sesi seminar. Kemudian pada workshop besok itu materinya akan diberikan oleh pakar ya, peneliti juga dari LAPAN ya, Lembaga Penerbangan dan Antariksa Nasional. Kemudian akan diberikan juga materi dari IPB ya, dari IPB Bogor. Ya, IPB Bogor ini saya kenal Pak Fakih, beliau sangat fasih ya di dalam melakukan pemodelan perubahan iklim ya, yang beliau dari agrometeorologi IPB ya. Beliau akan memberikan materi workshop besok. Saudara-saudara sekalian, seperti yang disampaikan panitia tadi bahwa ada kalau tidak salah 7 license yang akan diberikan ya. Yang pertama adalah license hari pertama akan diberikan sesuai dengan kriteria yang sudah disiapkan oleh panitia tadi ya, license RGIS. Kemudian hari kedua juga workshop akan diberikan 1 license. Itu kalau tidak salah ada 5 license yang diberikan pada saat seminar. Ya, ini luar biasa ya, karena kalau kita lihat harga 1 license RGIS ini sangat mahal ya untuk profesional. Saya bekerja sebelum di UNDIP itu di perusahaan swasta juga yang menjual ArcGIS ya, dan saya tahu persis harganya. Kalau harga terakhir itu kalau tidak salah ada 18.500 US dollar. Jadi lebih dari 200 juta harga 1 license. Jadi kalau misalnya salah satu peserta kita di workshop ini itu dapat 1 license itu, alhamdulillah ya, harganya bisa untuk membeli 1 mobil expander lah kira-kira. Ya, kemudian besok juga 1 expander. Kemudian hari seminar itu ada 5 expander seharga 5 expander yang dibagikan. Jadi luar biasa ini, artinya bisa menghasilkan door prize dengan demikian besar. Dan ini sangat membanggakan bagi kita, terutama di Fakultas Perikanan dan Ilmu Kelautan. Ya. Mudah-mudahan acara ini bisa berlangsung sukses dan lancar. Matur nuwun sekali lagi ya atas dukungan, bantuan, dan kerjasama yang diberikan oleh Fakultas Perikanan dan Ilmu Kelautan Universitas Diponegoro ya Pak Agus, sehingga acara ini bisa berlangsung dengan sangat baik. Ya. Demikian dari saya, terima kasih. Kurang lebihnya saya mohon maaf. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh dan selamat pagi.
Terima kasih kepada Dr. Muhammad Helmi, S.Si, M.Si atas sambutannya. Selanjutnya, sambutan yang akan disampaikan oleh Wakil Dekan Bidang Akademik dan Kemahasiswaan FPIK UNDIP, Bapak Agus Trianto, ST, MSc, PhD. Kepada Bapak Agus Trianto, ST, MSc, PhD, waktu dan layar dipersilakan.
Oke, selamat pagi. Assalamualaikum warahmatullahi wabarakatuh. And good morning, ladies and gentlemen. Because here is Prof. Sucharita, so I will give opening speech in words in gado-gado. It's mean a mix between English and Indonesian. Okay, it is my great pleasure to welcoming all of participant on the workshop of perubahan iklim dan pesisir. Our honorable keynote speaker, Professor Sucharita Gopal of Boston University. Good morning, Prof. Suci. Dr. Bambang Sukresno of Balai Riset and Observasi Laut. Selamat pagi, Pak Bambang. And Dr. Ahmad Fakih of IPB. And Dr. Emiyati of Lapan, and also Dr. Helmi, Supervisor of the Register. Selamat pagi. And all participants from whole part of Indonesia. Climate change has enormous effect on the environment. Millions of people are already suffering from the catastrophic effect of extreme disaster exacerbated by climate change, from prolonged drought in Saharan Africa to devastating tropical storm whipping across Southeast Asia, the Caribbean, and the Pacific. Jadi intinya adalah bahwa climate change telah memberikan efek yang luar biasa, ya. Telah menyengsarakan begitu banyak orang, menimbulkan berbagai macam bencana. Dan coastal adalah salah satu area ya, yang terdampak sangat tinggi akibat climate change, sehingga mengakibatkan banjir, rob, kemudian abrasi, dan berbagai kerusakan lainnya. Hopefully, kami berharap bahwa workshop ini bukan saja meningkatkan pengetahuan dan skill para peserta, tetapi juga dapat menciptakan or establish a global collaboration to resolve all the climate change impact. Jadi sekali lagi harapan utamanya ketika workshop ini adalah bukan sekedar ilmu pengetahuan dan skill, tetapi juga kolaborasi. Karena tanpa kolaborasi akan sangat sulit bagi kita untuk mengatasi permasalahan yang timbul akibat perubahan iklim tersebut. Dan akhirnya selamat berworkshop, semoga bermanfaat, bukan sekedar bagi diri sendiri, tapi juga bagi seluruh umat manusia. Have a nice workshop, and akhirnya terima kasih untuk panitia atas kerja kerasnya, dan wassalamualaikum warahmatullahi wabarakatuh.
Terima kasih kepada Bapak Agus Trianto, ST, MSc, PhD atas sambutannya. Baiklah, langsung saja menuju acara inti, yaitu penyampaian materi-materi. Materi pertama akan dibawakan oleh Profesor Sucharita Gopal, PhD dari Boston University, yang akan dimoderatori oleh Dr. Muhammad Helmi, S.Si, M.Si. Sebelumnya, izinkan saya membacakan sekilas biografi moderator pada materi pertama ini. Dr. Muhammad Helmi, S.Si, M.Si, merupakan Ketua PUI-PT Pusat Kajian Mitigasi Bencana dan Rehabilitasi Pesisir, CoREM, Universitas Diponegoro. Beliau merupakan ahli di bidang Remote Sensing and GIS, Water Management, Mitigation and Rehabilitation Disaster. Beliau menempuh pendidikan S1 di Universitas Gadjah Mada dalam bidang geografi, penginderaan jarak jauh, dan kartografi. Kemudian menempuh jenjang S2 pada tahun 2007 di Institut Pertanian Bogor, Indonesia, dalam bidang pengelolaan sumber daya pesisir dan laut, dan menempuh jenjang doktoral pada Universitas Diponegoro dalam bidang manajemen sumber daya pantai. Kepada moderator, waktu dan layar saya persilakan.
Ya. Terima kasih Mbak Rahmadiana ya. Slide-nya mungkin bisa maju satu ya. Ke Prof Suci. Ya. Prof Suci, are you with us? No?
I'm here.
Okay. Thank you very much.
I was just on mute.
Yes. Thank you very much, Prof Suci. Before we start, I'll try to inform the all participants and also our Vice Dean, yeah, Dr. Agus Trianto here, and also several other speakers that will be provided in our today's workshop and also seminar. Ya. Selamat pagi, saudara-saudara sekalian. Assalamualaikum warahmatullahi wabarakatuh. This morning we have a very smart professor, Professor Sucharita Gopal, PhD from Department of Earth and Environment and Center for Remote Sensing, PERDI, Center for the Study of the Longer Range Future, Boston University, yeah, in Boston, United States. I have here in our slide, we can see the expertise of Professor Suchi. The expertise is remote sensing, yeah, emphasizing ecosystem monitoring and land cover mapping, and also land use climatology, emphasizing land use, energy, and radiation balance. And the last one is data analysis and modeling, emphasizing applied problem in physical geography. Yeah, this is very important expertise that we need here in Indonesia. And Professor Suchi have several academic achievement. Yeah? PhD on 1988 from University of California at Santa Barbara, California. Yeah? Her PhD in geography. And he got his master MPhil in 1983 from Madras University, India. Yeah? Also master in geography. And also she has M.Si, yeah, graduate also from Madras, India, and his bachelor also graduate from Madras, India. Prof. Suchi will present and also will show to us about the geostatistic, yeah, especially kriging method to interpolate the data. Many kind of climate data must be provided using this methodology. Yeah, so the geostatistic is very, very important in our research. Yeah? And I have seen the Prof. Suchi slide. That slide is very detailed, yeah? And deep information and analysis. So I have informed to Prof. Suchi that Prof. Suchi should present slowly because commonly Prof. Suchi talk with the US or American student in English. So hopefully Prof. Suchi not forget that this session Prof. Suchi should talk to the Indonesian. With English is not our mother language. So please explain in slowly. I have informed that to Prof. Suchi before this session. Yeah? And also Prof. Suchi will show to us how to do that processing using ArcGIS application. This is very complete workshop that we have from Prof. Suchi. Okay, I would like directly to invite Prof. Suchi to the presentation, and after the session we will have a discussion, a question and answer, and Prof. Suchi can answer our question directly. So you can, the participant can asking many things related or maybe not related to this session. Yes, please. This is a very important time for us, and we are very happy to have a smart Professor Suchi to join with us this morning. Thank you, Prof. Suchi. The time is yours.
Thank you, Professor Helmi. Can you hear me okay?
Yes, very clear, Prof. Suchi.
Very good. Thank you all for being here and attending this session. It's my pleasure to speak to you all. I will try to speak slowly. I made a note for myself, speak slowly. And I want to get many questions from you. You should feel free to ask me questions. If you want, you can put it in the chat and Professor Helmi will let me know the questions, because sometimes it's important to ask the question and get the answer right away. Sometimes I can wait till the end, but I would like to take as many questions as possible as I am lecturing. So my talk today, and can I share the screen? Yes, okay, I can share my screen. Okay, I got it. So first I'm going to share one screen and I will enlarge the picture. Are you all able to see it? Can you see it?
Yes, yes, Prof. Very clear.
Okay, I'll try to make it as big as I can. So this is a lecture which is on the topic of geostatistics, and the particular technique is called kriging. It could also be called kriging. This was invented by a geologist in South Africa because people who are looking for gold, or even people who are looking for oil fields in Indonesia, do not want to go drill everywhere. They want to drill at a few points and try to make a map in order to understand where exactly is oil found or where exactly is gold found. So this technique is very important for mining and in petroleum and drilling. And I want to speak about this technique because it has got so many applications beyond the field of mining. It's used for climate data, it is used for estimating rainfall, it is used for assessing the price of a house, it could be used for looking at sea level rise in Indonesia and the work that I'm doing with Professor Helmi. that I will describe. So it has lots and lots of uses. So I wanted to bring this to your attention and talk to it from the point of view of ArcGIS. How does ArcGIS do this? And if anybody is also programming in R, there is also the free programming tools available for you. So I wanted to bring that to your attention. So what is geostatistics? So if I have a set of data points on my map right here, I'm collecting a bunch of points on a map. I want to create what is called a continuous surface. What does that mean? I want to take a point data and make it a polygon data in GIS. So in order to explain this better, I'm going to switch over and write this here so you can see what I'm trying to say. So you see, if I'm going too fast, you stop me. So I'm going to take point data in GIS and I want to convert it into polygon data. That's what I'm doing. So I collect point data from 30 observations, 40 observations, 100 beach points, in North Bali, and I want to make a map of the surface. The point data here could be rainfall. It could be sea level erosion. It could be anything that you're measuring, which is a continuous variable. So in GIS, we always make difference between natural variables that are continuous in nature, like rainfall, climate, soil, sea level erosion. And we distinguish that from data which is categorical, meaning I'm talking about urban, areas that are suburban, areas that are rural, agriculture, and so on. Those are called categorical data. And I cannot Krieg using those types of data, but I can Krieg with continuous data, which is more or less natural processes. And these come in two forms, ratio and interval. So these are all things that you learn in GIS at the beginning. So I'm just trying to alert you. Professor Helmi, is that clear? I'm looking at ratio and interval data.
Yes, very clear, Prof. Suchi, very clear.
So in GIS, I also frequently talk about the two big properties of GIS, which is to do with spatial autocorrelation and spatial heterogeneity. These are two things that all of you should know, because the only reason you want to do GIS, the only reason you want to get into spatial statistics, which is a big field, is because data in GIS has two properties, two very important properties. One is it is autocorrelated. So if you think about it, everything in space is related to everything else. So it means if one person in your town or dorm or a building has COVID, everyone else around will get a chance of getting COVID. That means we are thinking about the idea of social distancing, which is in COVID, you have to be 6 feet apart. And that's the reason you all can't sit together. So that idea is spatial autocorrelation, because all things in space, including COVID, is related to things that are around it. If one person is standing here, the person standing next to me will get COVID, right? So that is called spatial autocorrelation. Whereas you sitting in Indonesia, far away from me, are likely not to see COVID from me. You may get COVID from your neighbors, but not from me because I'm too far away. So that is spatial autocorrelation. Do you have any questions? Spatial autocorrelation describes many things. Everything in space is related to everything else, but things that are close are more related. So everything in space is related to everything else. So if one person has COVID, then people around him within 6 feet will get COVID. People who are 100 kilometers away may not get COVID from this person. So that is spatial autocorrelation. The other property I want to look at is the patterns in space. You see, all of the blue areas form a band, form a pattern. The green areas form another pattern. So patterns in space, so let me write the word, P-A-T-T-E-R-N-S. Patterns in space are described by this property of spatial heterogeneity. It's a very difficult word to say. Heterogeneity is the opposite of homogeneity. Homo means everything is similar. Hetero means everything is different. So we want to be looking at patterns in space, and that is also a fundamental spatial process that we want to describe. So when I look at the soil water in this sample, I'm seeing all patterns. They are blues and greens. And using GIS, I'm able to give colors and make a map that shows the spatial pattern or spatial heterogeneity of my soil samples in the study area. So these are the two things that I'm going to constantly talk about, because I need to keep emphasizing these two properties, because that's what is like the glue. Glue is like gum, things that stick together. That is the glue that makes kriging possible. I need to think that things that are close by, if a certain beach in North Bali, a particular site is eroded, it has a lot of soil erosion and sand erosion and the beach erosion, the area right next to it will also have erosion. But an area which is 10 miles south may not have that erosion spreading from this location. And that is spatial autocorrelation. We need to know that. And everything is dependent on the distance. In some cases, it's 6 feet. For COVID, it is 6 feet of distance. If I'm looking at beach erosion, it's not 6 feet. It could even be 2 kilometers down. Beach is a big thing. So you may see the distance at which spatial autocorrelation happens will change from one application to the other. And who's going to tell you what is the distance? Who will tell you? How do I know it is 6 feet and sometimes it's 6 kilometers? How will I know that? I have to consult with experts. I have to look at, literature that's already published by people. Professor Helmi, am I going too fast?
No, Prof. It's okay. It's okay. Yes.
So in GIS, do you teach about these properties? You must, right? When you're talking about GIS?
Yes, but not in deep, only in general.
Okay,
Yes,
so
this is very important.
I'm going to go deep, and you should ask me questions. You should definitely ask me questions. Hold me and ask me questions. So I want to go to the next slide, and I'll go back to my PowerPoint presentation. So I'm going to the next slide. So this one shows you not a natural process. It is showing you house price in different parts of some city. It is showing you there are areas where it is, property value is higher The very dark red here in the middle of this map, the property value is very high. When I'm looking at something which is like shaded like this, these kinds of light colors, the value of the house is much less. So you are able to use this kind of geostatistical technique and make a prediction for the value of a house everywhere, because you have a few samples and you can use geostatistics to create a big surface. So I may not have the data because I wouldn't know every single house in the neighborhood that will have a price. Every part of Jakarta, every part of Semarang, I wouldn't know what the rent is. I wouldn't know what the value of the property is. I would be able to do this using kriging because I'm taking some samples from various points and I'm making a nice map. So this is called inference. I'm able to estimate and make a map. And this is very important in GIS because I don't need to have data from every point in Semarang. I can know a few houses and I can make such a map. That's the other property of geostatistics. So if I am looking at the application, and this is the one I want to show you in terms of an example, I'm looking at this particular example shows California, and it is showing you the California map in terms of episodes of something. So in this particular case, it is showing you ozone. Ozone is a very bad kind of a pollutant in the air. So I'm collecting from the green dots. I am getting air pollution data. And I want to make that map, which is shown in the background from red to blue. So this is the data that I have. And I make this beautiful map that is in the background of reds to blues. And I'm using geostatistics to make this map. And using GIS. Any questions?
Not yet, Prof. Suchi.
Okay.
I monitor in chat, but
Okay.
maybe later. Maybe later. You can continue. I will interrupt you if any question.
Good. Thank you.
Okay. You're welcome.
So in this particular slide, I am looking at one of my students who is just like you. He could be an Indonesian student. So I put Evan Friedland and I put Indonesian student. Just to tell you, you could be doing this, right? I'm making a joke. You could be doing this. So this particular data set is thousands of data points. And this is actually oil fields and natural gas fields in Texas. This is called shale. Shale is a very important way, and the word shale is written here. Shale is a very important rock layer and geological formation that produces natural gas. So in the United States, they do a lot of this thing called fracking. The whole process is called fracking. So if you Google it, you will see what it is in Indonesian, in Bahasa. So let me see if I can write the word for you. So this has become very serious in the United States. It's called fracking. So even in politics, both candidates of both parties talked about fracking, that they will allow fracking in Pennsylvania so they can employ people and drill for natural gas. So what we did in this exercise is to take all the points where they are, mining and looking for natural gas or oil, and we wanted to make a map. So we could make predictions of oil wells in all other locations where we did not have the data. So the geostatistical technique helped us to make predictions of where is it that there is oil all over this region. So that's the student who could be an Indonesian student, giving that kind of answer. So I don't have to go into the details. I'll leave you to read it because we gave a lot of background there. Now I want to go into geostatistics. So first thing is, what is geostatistics? What exactly is kriging? So this is a class of statistics that can be used to analyze and predict. Predict means I can, get to know the value of things that I didn't know before. I can predict the values associated with spatial data. The geostatistics also means I can describe spatial pattern. Remember the word for spatial pattern? It's spatial heterogeneity. I can describe spatial heterogeneity, and I can interpolate values for locations where there were no samples. So I can also provide measures of uncertainty. So I could be looking at points of beach erosion in North Bali and make a prediction for the entire north coast of Bali using geostatistics. So this kind of data is collected by Professor Helmi. So obviously we can do such an exercise with you. So geostatistical analysis has evolved from univariate. Univariate means one variable at a time. Like I'm looking at oil, or I'm looking at temperature, or I'm looking at house value. Now these days, you can do what is called multivariate. That means I can look at home values, number of trees, proximity to transport, airports. I can put in a lot of different GIS variables and make it a multivariate analysis. So that is geostatistics. So the next slide, I walk into, where did it come from? So it came from the field of mining, because they were trying to mine, look at, what is the economic feasibility? I don't want to go drill holes everywhere. I want to drill holes at a few points and make a map. So I know where should I be looking, because it costs me a lot of money to go drill many holes, right? So if I am looking for oil, I have to go very deep. I have to put a bore well and go all the way down. And the more depth I go to, the more costly it is, more expensive it is in terms of rupiah. So I need to be careful that I don't spend too much money. So I need geostatistics to tell me at what depth should I go and where should I be drilling for oil, because I only have a little bit of money and I need to make very good use of the money. So that means I need geostatistics to get me the information. So it's used everywhere now, environmental health, and other applications. And I can talk about it if you're interested in any one application. Okay, this is how the geostatistics workflow looks like in terms of a GIS problem. First, you would map and collect all your data samples, look at your data. Second step, you would pre-process the data. You have to statistically do all kinds of transformations, finding the distributions and so on. Third step would be you want to look at the spatial structure, which means you're looking at the spatial pattern or heterogeneity. Then you need to sort of look at a little bit of what exactly should be the spatial distance at which you want to look. Then you want to make a prediction for unsampled location, that's 5. Then you want to be able to say, what is the confidence that you have in predictions? If you were to say this part of the coast of North Bali has beach erosion, you need to provide confidence. You have to say, I'm 99% confident that the beach is being eroded.
Excuse me, Prof. Suchi. Question, Prof. Suchi.
Yeah.
Yes. Yeah. Okay. This is a very interesting question from Auliana Fikri. This is in Bahasa, but I'll try to translate for you. Is there any regulation or any, what do you call that? Yeah, something like any convention or regulation about how many points that we need to process geostatistic according to the area that we want to interpolate, something like that. Thank you, Auliana. Yeah.
Right. Oh, this is a very good question. Whoever asked me the question. Excellent question. So in general, you want to have as many data points as you want. But in terms of statistics, you need to have, if you're going to use something and you don't have the money, you don't have a lot of, ways to collect this data, you would need at least a minimum of 30 points, right? And you need to be looking at what is the statistical test you want to do. If you're using a t-test, you need 30 points. But in order to capture the variation, you need a lot more points. So it's a question between the expense of getting the data and what is statistically the most viable, kind of a sample. So there is no answer other than this magic number of at least 30. But you need to, if you have money, collect as many points as you can. Because the more points you collect, the better is your confidence in prediction. And you also need to make sure you capture the variation. Let's say I'm looking at Indonesia. In Indonesia, you are an island nation. Island of Java is very different from Sumatra. Sumatra is different from Borneo. Borneo is different from Kalimantan. All these islands have different geological histories. There are 3 different geologies in Indonesia. So you need to make sure that you get all of that if you're studying a big area in Indonesia, all of Indonesia. If you are looking at the beaches in North Bali, I can get away with 30 samples because I'm only looking at a stretch of a beach. Any other question? That was very good. That's a sampling question.
Yeah, thank you. Thank you, Prof. There is another question, Prof. Suchi. This is very good question also, I think, from Novia Safina Tunajah.
She's not from UNDIP? You don't know her?
UNDIP, yeah.
Oh, she's from
She's
UNDIP.
from, yeah, Novia Safina Tunajah. Very good name also. Yeah. The question is, what is the impact of the pixel size according to the result of the geostatistic?
So
this is very good.
Very good question. So if I'm converting it into a creek surface, and I'm going to talk about it also towards the end. So when I take a point and I make a surface, there is no pixel associated with it. It's a continuous spatially varying surface. I can impose a pixel on top of it. I can impose a grid on top of it to make it a raster image. And in order to do that, I need to know what's the total area, what were the points, and what would be my choice of a cell size. If I take the cell size to be 30 meters, like let's say Landsat resolution, I need to have enough confidence that it is showing a lot of spatial variability. that it is capturing spatial heterogeneity, the pattern. If the map looks very coarse and it has lots of few colors and it's like spread, it's a much bigger area, like a world map that I've done the geostatistics on, I have to take 1 kilometer or half a kilometer resolution. So it depends on your total area. I could go anywhere in terms of pixel size. And these days, everybody goes with, pixel sizes that are similar to the satellites. So 30 meters is a good choice if it's a small area. So we just did work on Southeast Asia, looking at forests and deforestation in Indonesia. I'm doing a paper with a student, and we are looking at biodiversity in Indonesia, and we are looking at it, all of Indonesia at 30-meter resolution. So that choice depends on how big is the area, are you using a satellite sensor, what makes sense. If it is the world scale, you can't do it at 30 meters. Your computer will just go into flames, right? It should be at half a kilometer or 1 kilometer.
Yes, thank you, Prof. Suchi. Very clear explanation. You can continue.
So now I want to ask you that I'm going to check the model. And if the model in step 7, if it produces a good, reasonable surface, that I'm looking at it and going, hey, it makes sense, I would sort of proceed to step 8. And I would take a decision based on that. But if I was not happy with my answer, I can go in and redo my data. I can get more samples. I can think, what did I do wrong, such that my map doesn't seem to, give me the, confidence that I want. So there's all kinds of ways of testing statistically the confidence that you have. Step 7. And I can proceed to step 8 if I'm happy with step 7.
Excuse me, Prof. Suchi.
Yeah.
There is a student with the raised hand. I think she will asking a direct question.
Oh, sure.
I'll try to invite Dwita Octave. If you,
yes, sir.
You would like to ask something to Professor Suchi, yes, the time is yours.
Okay, thank you so much for your time, because I want to ask about the question before. I heard that there are many benefits that I heard earlier. So my question is, are there any limitation for this method, ma'am?
Are there any limitations for this method of geostatistics?
Yeah.
So the limitation is the uncertainty in prediction in step 7. I may not be happy with what I see because I don't have enough data points. I got a bad map. So every technique has problems, and it's better to know what is the problem, what is the confidence that you have, and you may need to go correct it or just say, this is not working, I will use another method. But this particular method, geostatistics, even in ArcGIS, has many variations. So some of the 16 different methods that they have will be good enough for you. So, and in GIS, you can do 2 types of analysis. One type of analysis is called just data exploration. You just look at the data, try to understand what is it that you're looking at. Is there any spatial heterogeneity? Can you make a predictive map? If your only goal is to just describe what is happening out there, you're fine using geostatistics, even if it doesn't work. If you want statistical inference and you want to make predictions and you want to have confidence, then you need to make sure that it answers that question. So you can do GIS 2 ways. You can explore the data, which means you're not concerned with prediction, or you can use statistics and make predictions.
Yes. Okay, Dwita?
Yes, sir. Clear enough. Thank you so
Yeah.
much.
Okay.
Oh, you're
Okay.
welcome.
Thank you, Dwita, with the very good question. Prof. Suchi, I have another good question here from Mario Limbong. Yeah? I think he's not from UNDIP. Very good question here. When do we use kriging and IDW? This is the different
going to
type
come
of
to that.
kriging.
Yeah, yeah.
Yes.
I am going to talk
When
about.
do we? Yeah. When do we use kriging and IDW to interpolate data? What is the difference from analyzing terrestrial and oceanic data regarding to the first question? Yes.
So I am going to
And
talk about it.
okay, okay. Jadi Mario Limbong, Prof. Suchi will explain your question in the next slide. So I think we should wait on that, and after that, Prof. Suchi can explain to you. And I can continue with the other good question also from Reynov Razaki. From, this is UI means Indonesia University, maybe in Jakarta.
Oh, in Jakarta.
Reynov, yes. The question is good, very good presentation, Professor Sucharita. I want to ask you about the geostatistical method such as IDW and kriging. What is the difference about IDW and kriging in interpretation of geospatial analysis, and which of these two methods is easier to use? This is also related to the question before. Almost similar. I think Prof. Suchi will explain this later. And other question, Prof. Suchi, this is from the student also. What is the best method that you recommend to take account spatial autocorrelation? This is from M.Si from LAPAN. LAPAN is Indonesia Space Agency. So this is something like a NASA in US. Yeah. Thank you, Ibu Emi. This is very good question. The question is, what is the best method that you recommend to take account spatial autocorrelation? Yes. This is from the government staff agency from Indonesia Space Agency in Jakarta. Yeah.
So so now we are like expanding and going everywhere. So if you want to look at, I'm not focusing so much on spatial autocorrelation in terms of testing. Spatial autocorrelation, you can do a test called Moran's I, and you can also do something called IK key information criteria. And I can describe that because that is not directly connected with interpolation here. Spatial autocorrelation just measures if things are related in space, right? It looks at what is called hotspot analysis. And I will keep that aside because right now we are focused more on spatial pattern rather than autocorrelation. So I'm going to talk about this and I'll come back to answer that question later because that's not connected with what I'm talking. So you asked me about inverse distance weighted method, and inverse distance weighting is very, very simple. Anything in space, as I told you, and this is called Tobler's law. And you can also look it up. Let me see if I can. I'm also going to do some math with you. I'm going to make you calculate. So I'm going to be talking about Tobler's law, which said, and I'm going to write this, everything in space is related. things that are close, oops, sorry. Things that are close are more related than things that are far away. So this principle of Waldo Tobler, who was a professor in UC Santa Barbara, who's probably one of the big people in terms of cartographic mapping, and he's phenomenal. His law is what is used for inverse distance weighting method. As you increase the distance, the spatial effect or spatial autocorrelation falls off. It comes down like that in a curved form. And that's what you use for inverse distance weighted. The weighting is, as distance increases, it's going to have less and less and less weight. Things that are close, they'll have a larger weight. So that's why it's called inverse distance weighted. So it says, this has got no biological explanation. It's got no physical meaning. So it's just a relationship in which all things are related, but close things are more related than things that are out there. And that's Waldo Tobler's law. So inverse distance weighted method is the simplest method. You just want to try it because you want to see how does kriging do in relation to inverse distance weighted method. Inverse distance weighted method is not based on anything. It's just based on distance. It's like, something very simple. You want to say when you move away from a person who has COVID, you're not going to get COVID. That's all it means. It's not based on anything bigger than that, right? It's not a theory. It's not anything beyond that. So most people prefer to try inverse distance weighted method as step one, as the first step in the analysis before they go to kriging. Did that make sense?
Yes, Prof. Suchi.
So now I want to show you an example of how I would do inverse distance weighted method, and I'm showing you the formula. So I have a set of points, 1 to 6 points. Each of the points has an x coordinate, y coordinate, and a z value, which could be the depth of the ocean, it could be the soil, it could be the temperature, it could be anything that I'm measuring. And I want to use the inverse distance weighted method to calculate the answer for predicting what is the value at A. Remember, I only know 1, 2, 3, 4, 5, 6 points and the Z value. I want to make a prediction for the value of Z at location A. And since it is using this method of nearest neighbors and weighting it more, I should be able to make a very simple calculation. The formula says that f of, the value at any location R is half of n. N is the total, number of points in the distribution. And it's saying, take the value of the neighbors of X, all of the neighbors, distance from A to D, distance from A to point 2, point 3, point 4, point 5, point 6, and estimate the values of all this and, take away from it the X-Si. So let me see the calculation on the next slide. So if I were to look at it and I were to, bring the previous map here so as to make you see it much better. So if I were to look at this in terms of this map, I'm going to measure the distance at point A, which is located at 2 coordinate and 3. So point A is 2 and 3 X and Y coordinate. And I want to look at the distance between point A to all the 6 locations. So here is my calculation based on the formula that I saw. It says, take the distance, take the value of the z, right? The value of the distance between point A and 1. I have to look at the distance, and the value of z at 1 is 40. So the distance between A and 1, if you look at it, is a Pythagorean theorem. It is 1 squared plus 1 squared. And the distance between the two is the square root of 2. Square root of 2 is 1.414. So it takes the distance of 1.414 multiplied by 40, and it's the inverse distance. So that means I have to raise it to -1. And I add the next point, which is number 2. The distance between A and E is also a Pythagorean distance of 1 squared plus 1 squared, which is the square root of 2, that is 1.414. Distance between A and 3 is easy. It's a distance of 2. So take a look at it. Distance of 2, inverse distance of that, multiplied by the value at 3, which is 30. The z value at 3, which is 30. I finish the calculation and I get a numerator value of 102.16. The denominator value is just the inverse distances of all of the points of A's neighbors. And that happens to be 3.47. So if I divide one by the other, 102 divided by 3, I get a value of 29.36. So 29.36 is the value of z at location A. That was estimated using inverse distance weighted method. It is as simple as that. So we were able to do this because it's a very simple example. What happens if you have more than 100 points? You can't be calculating this by hand. You need a computer. And that's why GIS is very handy, because I can throw into a computer package 100, 500, 5,000, 10,000 points, and it would calculate, these distances of all the unknown locations in multiple ways. And once I have all of the points made, I can go in and create a surface. So inverse distance weighted method is the simplest method to estimate locations, the value of z at locations where we had no value. So you can do this very simply by using this formula. Let me show you another example. Here I'm trying to calculate the location that I'm showing right here, and I'm taking the distances and the value of z at various locations. So it is, if you look at the value right here, the distance between the red dot and the green dot is 1. So I have the distance 1 squared, which is the inverse distance, and 34. I can take all of this in my numerator just like I did before, and the denominator is the inverse distance of all the distances: 1 squared, 2 squared, 2.5 squared, 3 squared, and 4 squared. And I have all this calculated to give me a value at this red location to be 32.38. So that's how inverse distance weighted method sort of works. So I want to show you where has it been used in terms of distance weighting. So people have looked at Chernobyl disaster in Russia and Belarus. Right here. There was a big disaster in Russia in the 1980s. This was made into a Netflix movie. So if you get a chance, watch it. It's not an entertaining movie. It's about this Chernobyl disaster, nuclear disaster, that probably led to the death of many. And the whole Chernobyl area was shut down for more than 30 years. And they just made the movie. because it's 89, 99, it's more than 40 years or whatever. You can do the math. But they made this movie to show you the impact. All the trees around Chernobyl, everything died. All the birds died. All the animals died. And the people were not told that there was a nuclear disaster. And it took them a long time to move away from the area. They all got cancers. A lot of people died because of the nuclear reactor and the explosion. So this is a nice, somebody made a map. It's not a nice map, but it shows you the disaster and how they made predictions of the spread of the nuclear, pollution that spread all over, the radioactive waste that went all over. So they have studied the radioactive air pollution, what happened, and they also studied the on-the-ground radioactive pollution. And that's the map. And this was done using distance weighting, but you could also do a kriging. This paper actually looks at soil contamination levels. So this is not air pollution. It's soil contamination in Belarus, which is a country now of the power plant disaster. And it looks at what happened. So you can immediately see that there's a variety of colors. And although the disaster place is right here, the most soil contaminations in red are shown in this part. So must be there is some way, there is a river or there is some underground passageway by which all the pollution went here into the soil. Or maybe the circulation of winds goes this way. So the wind carried all the material to this part of Belarus. So this entire paper is about looking at spatial interpolation and looking at distance weighting for predicting this kind of a disaster. Okay, so that is the very simple stuff. Now we want to get into, and here I mentioned Tobler's law and spatial autocorrelation. So now I want to talk about the, and I think I described this, and I will talk a little bit more about this. So why do we need to use geostatistics? Geostatistics will help you characterize or describe spatial autocorrelation. Spatial autocorrelation is a function of distance as well as the direction, like in Belarus. The soil contamination happened to the southeast. So this is very important because usually I do not understand at what is the distance at which the spatial autocorrelation function levels off. But using a variogram, I can tell you at what distance do I have to stop. My relationship is falling off or there is no more COVID spread. I want to be able to take locations and create a continuous map. That's the second use of kriging. I also want to be able to simulate the many realizations of the data set. And I want to make a statistical model and build a very strong model such that I have confidence. And I don't know if I will have time to get into the third one, but I will try. So if I look at a bunch of points, usually I use a linear regression equation to think about what is the fit of the model. I'm trying to look at all these points and I'm trying to look at how do I fit the model? And I'm always using this straight line linear trend estimator to describe the fit. And there are many other models. For example, you could make different model called the spherical model. And I will discuss all this with you in going further in this type of estimation. I also want to look at the residuals, which are the error terms of what did my geostatistical model predict and what did I observe, and what's the difference between the prediction and the observed values. And this is where Moran's I, which is a test, comes in. I'm looking at the fit and I'm looking at the residuals. As far as possible, you want all of the residuals also to be around this line. You don't want to have these. These in statistics are called the outliers. So let me write that down for you. See if you know the term. In statistics, these things are called outliers. And I don't want to have such large outliers. I want prediction to be very tight. But I will go on and we'll come back to this point again. So we also hope that all of these residuals are fit in a certain way. They are fit using these plots, which are called quantile plots. And I want to look at the histogram of the residuals. All of these errors that I get out of the model of my prediction should have some distribution. In statistics, that's very important. And I should be able to plot all this using what's called a quantile plot in ArcGIS or in statistics, and I'll show you that. So if I'm sort of, going to be testing, I could be using Moran's I, and I could be looking to see what exactly is the nature of my prediction. And I'll come back to this once I explain a few other things. See, in variogram, I'm always looking at prediction. And so when I look at the next slide, this tells me what exactly am I trying to do. So when I plot all the things, which is the top graph of population counts, and I were to translate that into a variogram using this kind of spatial autocorrelation idea of geostatistics, I would get these pink lines, which are the fit. If I create this kind of line, this particular distribution, red points here, there is no spatial autocorrelation. Absolutely. It is flat. There's no spatial autocorrelation in that data. If I look at something like this, there is some spatial autocorrelation because I have an intercept term here and the curve is increasing, then leveling off. This has got a high degree of spatial autocorrelation. It starts at the origin point, increases, and goes levels off. So I can look at whether the variogram produces a flat line, which means there is no spatial autocorrelation, or whether there is a gradual increase and a flattening out, or whether there's a steep increase and flattening out. So these are fundamentally the three things that I'm likely to see in the variogram. I want to describe the properties of a variogram. Okay. So if I were to look at, and I'm going to come back to the formulas, if I were to make a variogram, on the x-axis, I have the distance between pairs of points. And on the y-axis, this axis, I have the semi-variance of the distribution. And I'm going to write this in English. I think you all know what it means. And I will ask you that. The semi-variance is plotted on the y-axis. The distance between pairs of points is plotted on the x-axis. And I'm creating this variogram, the pink line. And those green points are the points for which I collected the data. So obviously, what it is telling me is that there is some spatial autocorrelation. And it tells me at what distance does the spatial autocorrelation begin, right? And this area here is called the nugget. This is noise factor. I can only start from this point. If this pink line went all the way to the 0, there is no nugget. I have perfect spatial autocorrelation. Here I have some noise. And so that is the nugget effect. Then the line is beginning, increasing, and it's leveling off. This particular distance at which spatial autocorrelation stops or it levels off is called the range. And I'm going to show you that. I've written everything down, so I'll show you that. And there is also another term called SIL. SIL is the value of the variogram. So let me show you the next slide. So the nugget will indicate the noise in the data. And you cannot reduce it or get rid of it because this is the distance at which you're not able to make certain that spatial autocorrelation is happening. You can only start at a certain distance. SIL is the distance, SIL is the model measure that explains the amount of variance that is explained by the model. And it's measured in terms of the semi-variance or the variance, the component of the variance on the y-axis. Range is the distance at which spatial autocorrelation is happening. You remember you asked me the question, at what distance would it stop? Range tells me at what distance spatial autocorrelation levels off. There's no more. And I would know I have to stop there, right? So as you can see, in terms of COVID, they first said it is 6 feet of distance that you need to have to your neighbor. And they marked all the areas, 6 feet, they put like little spots in the airport. Now they are saying that it could be 12 feet. If a person coughs, it can go all the way to 12 feet to the COVID virus. So that is the range. That is the distance to which COVID can contaminate. So that is the range, the distance. SIL is the amount of variance that I'm measuring at that leveling off point. What is the maximum value of variance that the model is explaining before it levels off? So I can sort of look at these statistics and draw a lot of different conclusions of my variogram. So I am going to go back to a few slides. So this slide, any questions? There are 3 types of situations. One type, when you draw the variogram, there is absolutely no spatial autocorrelation. In another type, there is a lot of noise and it leaves this much of intercept value and it begins here. It's not starting at 0. Here, it is starting at the 0th point. This is the maximum spatial autocorrelation. It has no noise, no random effects. So I'm going to stop here and let you think about it. And variance is nothing but standard deviation squared. In statistics, it is called the second movement. So in the first order of statistics, you calculate the mean, the median, the range, and so on. The second order of statistics, you calculate standard deviation or variance. And this tells you the variance on the y-axis is the variance that's happening in the distribution for pairs of points at certain distances. So if I'm looking at 100 points, maybe 50 pairs of points are separated at distance 2. And I need to go calculate the variance of that distribution. 10 points are at a distance of 40. I need to go calculate for the 10 points at 40 distance, what is the variance? And I plot those values on the y-axis in order to get this fit. Do you look at this kind of variance and semi-variance in your classes in statistics?
No, Prof. Suchi, not yet. That is quite deep or detailed, what do you call that, information. We give a lecture in more general because the GIS is combined with the marine science context.
But
This is
for
very,
students, yeah.
yes, this is very interesting, Prof. Suchi,
No,
because
for students, Professor Helmi, excuse me, for students, it's important that they understand the statistics really, really well, because they're going to apply it and you need to know what it means. You can't
right.
just play with ArcGIS. You need to know what you're doing.
Yes, correct, Prof. Suchi. Because
You
on
ask me
this,
questions because this is very important that you get it.
yes, because this is the overlap science between statistic and GIS.
Yes.
So in this overlap section, how to use, how to predict the location based on the statistic in the GIS term or in spatial term. This is very interesting, Prof. Suchi. I'll try to check in the chat. Not okay. This is a good question from Rainov Razaki.
Oh, where is Reina
Yeah,
Prasad?
Rainov
See
Razaki
you.
is UI, I think, Indonesia University in Jakarta. Yeah.
Oh, okay. Nice to see.
And yes, and another question, I think, from marine, what do you call that? Marine and Fisheries, Ministry of Marine and Fisheries, yeah, in Pontianak. From also the question is from Urai Rido. This is a good question also, and I will read for you. He has two interesting questions. Okay, I'll read the one first from Reno Frazaki, Indonesia University. Yeah. What is a characteristic good model of variogram based on Najet, SIL, and range? If the model have Najet, is that good? That is from Reno Frazaki. Yes, please, Prof. Susi, the first question, and after that I will continue with the others. Yeah.
Right. So we have barely started. There are many, many, many variogram models. This is the simplest model. So I need to compare against the whole set of models before I make a decision which model I want to use. I'm just explaining the terms that there is SIL, there's nugget, and there is range that you have to look at when you are exploring the data. I haven't sort of told you about this, choosing one particular model, because there I have to talk about local kriging, universal kriging, ordinary kriging, simple kriging, and so on. There are like 10 different kriging models, and I'll have to choose one of those models. This is just the explanation of what any kriging would give you. It would describe any one of these. And you will have to decide whether in your model you want to have the highest kind of spatial autocorrelation model in order, and you would prefer this type of a model. Or sometimes, if you don't have a good fit, you may sort of be willing to take some nugget value and you would try to look for the minimum and you would take this. But these are not the only models that are out there. There are many other models. And I'm coming to that in terms of explanation. What was the other question?
Yes. Yeah. Thank you, Renov. Very good question. Yeah? I think Prof. Suchi have explained that question. And Urai Rido, this is from Marine and Fisheries, Ministry of Marine and Fisheries Agency in Pontiana. Yeah, Pontiana is in Kalimantan, Prof. Suchi.
Kalimantan.
Oh, yeah, very far from here. And very interesting presentation from Professor Sucharita. Thank you for the opportunity. I want to ask few questions. I did some trial of geostatistic analysis. For example, water quality, that is include several parameters which are composed by using interpolation also. I have two questions about this. The first one is there any increasing misvalue possibility as we use more number of interpolated data to generate the derived target value, in this case, water quality? And the second question is, I realize as I choose several scenarios of different contribution of samples, it will result in different value or different interpolation value, and even the different is very tangible. So what is the critical factor to decide the distribution of our sample? Good two question, Prof. Suchi.
Yeah.
Can you catch the idea, Prof. Suchi?
Yeah, I get the idea. So he's asking, you may be producing different models using different techniques. And the question is, which model would you choose? And in all of these geostatistics, there are statistical tests that you can use to pick the best model, statistically speaking. And those are the kinds of things that I want to talk to you for the rest of the lecture to bring you up to speed. So before I do that, let me answer the previous question by also showing you a couple of other things. So one of the things in geostatistics is not only does it give you interpolation and variation in distance, it also tells you what direction is important in terms of, the variance changing. So this particular property is called anisotrophy. So if I'm looking at the ocean waters of Bali, of North Bali, and I'm looking at the pattern of ocean currents, I would expect certain things to happen in certain directions. You were showing me, Professor Helmi, arrows of wind going from, or ocean currents going from west to east, even from southwest to northeast, very fast currents. So if you were to make predictions and you had those values, it would have to model for you the directionality also of prediction. So this is another thing, a variogram. You only focus on distances, but it could also show you what is the relationship in terms of directions. And this, I think, is very important in Indonesia because it's a country of islands. It doesn't necessarily mean that certain things are happening everywhere at all distances. A country like the United States is very large. I'm not so concerned about looking at it in terms of directionality because it's a big shape. Indonesia is islands. So I'm more concerned about directions of the different islands. So this is a very good property to keep in mind, and I will let you sort of read it. So I can make plots and I can say the variogram is going south to north. One variogram, the directionality is west to east. And I can describe things that are happening in the field in terms of not just the distance on the x-axis, but also direction. So in our case of North Bali, Professor Helmi, I would be able to say the wind is going from, west to east. or the wind is coming from north to south. So this, I think, is a very important sort of thing for ocean sciences, especially for Indonesian ocean sciences, looking at coral reefs, looking at, salinity in the ocean, looking at, temperature of the ocean. It would be pretty good. So I want to talk about the questions that you guys raised. Variogram is very similar to some of the other measures of spatial autocorrelation, where I'm using Moran's I. Moran's I varies from 0 to 1, -1 to 1, but usually between 0 and 1. 1 means it's a perfect autocorrelation, spatial autocorrelation. 0 means there is no spatial autocorrelation. And if I were to use other measures of Moran's I, I could even describe negative spatial autocorrelation and positive spatial autocorrelation. I don't want to talk about it. That's not my lecture. So I just want to stick with the fact that variogram is very similar to Moran's I and Geary's C. And since I don't have time to talk about these things, it's a different lecture. That's a different topic. So, Professor Helmi, we need to talk about how to do a very technical GIS with students. And we'll do that later. I have ideas.
Okay. Okay.
So I want to talk about examples now. Let's say I have a lot of remote sensing data and I have 79,000 pairs of observations using a remote sensing image of 400 by 400 cells. And I'm estimating the differences in terms of distances between pixels, and we want to group similar pixels and try to understand the variogram. So the mean distance is 0 to 12, 13 to 24, 25 to 36. The number of pairs of points in my remote sensing 400 by 400 image is I don't have any in terms that are separated at a distance of 0 to 12, whatever I'm observing. My observation only goes from 13 to 24. I have 1100 pixels that fall there. In the next class, I have 2300 pixels that are separated at a distance of 25 to 36. And I'm calculating the square distance and I'm making a plot. This is what it looks like. I'm looking at backscatter and I'm fitting a spherical model. I could sort of look at what is the pairs of distance, and I'm looking at it on the x-axis. On the y-axis is the semi-variogram. This is my nugget. Between here and 0 is my nugget. It's almost about 600 units is the nugget. And the distance of the range at which things are leveling off is I need to look at this distance. It's almost, if this is 50, this is 100, I could say at a distance of 80, things are leveling off in terms of this line. And I can also tell you that at a value of 800 or 850 is the value of the sill at which the leveling off is happening. So I'm always looking at a variogram from the point of view of the nugget, the range, which is the distance, and the sill, which is my variance. And I can make a prediction of all of these. And that tells me something about the model and the fit of the model. I want to also tell you that you can make these values into three-dimensional surfaces, and they look very, very pretty in terms of looking at it in more clear ways. So the benefits, obviously, it's a very good tool for summarizing spatial data. It takes into consideration spatial autocorrelation or spatial dependence. And you can also calculate values of Z at unsampled locations. And I want to sort of describe to you a couple of different things. And in terms of kriging, we are always thinking that the kriging should be a prediction that has to be blue. Blue in statistics means a best linear, unbiased estimator. I want to make use of this principle called blue to make the estimation using kriging. And I want to sort of talk about different types of kriging. The first type of kriging is called global kriging. There are many types of kriging. I'm only looking at a few. In global kriging, every point in the distribution is used to make the surface or estimation. That means I'm not looking at spatial autocorrelation. Every point is included in my analysis. So global kriging is very useful if all the points in your distribution have an impact. But it is very time consuming to calculate. The computer will take a long time to calculate the estimation based on global kriging. So you need to sort of see what is the payoff, what is the trade-off. Can you put up with a lot of time, consider all points? What does that fetch you? What is the advantage? You need to think about it. In the case of Belarus and Chernobyl, I want to look at the soil contamination all over Russia, all over Belarus, because I know that is very important to understand the spread of radioactive waste. Generally, that's not the case. When I'm looking at this kind of study of ozone, I may want to look at it locally, not globally, because the air circulation patterns. I would not want to do this globally. In local kriging, I'm going to define the neighborhood function. I'm going to say neighbors within 1 mile, neighbors within 2 miles, within 10 miles. I could choose any neighborhood, but I want to only look at those neighbors in order to calculate this local kriging. So local kriging in some ways is the opposite of global kriging. It makes it easier because I'm able to look at processes at a much more finer and finer scale. So I'm mapping my ozone concentration, looking at local kriging right there. And we may use a range of data for local kriging. I don't know what window you want to use. Then there is also something called ordinary kriging. Ordinary kriging will estimate the mean of the distribution in order to calculate the values, and it uses the mean in order to estimate the value. And so there is another type of kriging, and absence of all other knowledge, if you want to ask me what kriging you should use, I would say use the ordinary kriging or the kriging that we discussed before, which is local. There is also something called point kriging, which is very useful for point data because you assume that the values are points rather than, a whole bunch of, samples. They're coming from different points. So that is point kriging. Block kriging is used in remote sensing, and that is also used in mining. It takes chunks of the Earth's surface and looks for creating a surface. So those are called block kriging estimates. And we generally don't use block kriging in much of GIS because very rarely, unless I have shale and oil and gold, I'm not going to use block kriging. I'm probably going to stick with ordinary kriging or local kriging because these are very simple. I don't have to even tell you why I selected ordinary kriging or local kriging. Whereas I have to tell you why I chose block kriging or any of the others in greater detail. There is also another kriging, which is the universal kriging. And that again is pretty sophisticated because it takes the estimate of the mean drift of the surface. So in statistics, this is a very complicated kind of concepts, and it uses all kinds of very sophisticated models to model the autocorrelation or the local neighborhood. So ordinary kriging is a special case of universal kriging. And so a lot of people prefer ordinary kriging. And the universal kriging, you need to know a lot more about your data, because it is going to use a stochastic error term. And I won't get into it because it's too much, in terms of details. So in kriging, you also asked me the question, how do I know what model should I be using? Where is my results the best? So there is kriging diagnostics, which is called cross-validation. So you remove one data point at a time and you make an estimate with the remaining data and keep repeating it 99 times, 1,000 times. And you would see what the estimates look like over the 1,000 data points. And that's another way to generate a distribution and compare whether you're doing okay. So this is cross-validation in terms of diagnostics to check which particular kriging you should use. And there is also kriging estimation of variance, and you can make all kinds of statistics on top of the kriging estimates. So here are some examples. This is from ArcGIS, and I can run an exercise and show you what it looks like. Maybe I should do that. So this one I really like because it shows you the fit in different directions in 0 degrees, which means I'm looking at the eastward direction. 90 degrees, I'm looking at westward. 45 degrees is up north, 135 is down south. And it produces different plots. It shows you there's something interesting happening in the many different directions of the coordinates. And the Krieg map finally would look like that. That's the surface that it's going to produce. And here is another one that my students made at some point. This is the contamination in well water in, I think it's Florida. And it is showing you the Krieg surface map. And I could also draw contours to make the map look nicer. So these are the kinds of applications we've used it for. And then I want to go into, so when I produce a kriging result, these are the types of models I have. Any type of model, you have to describe what is the function that you're using as the best linear predictor. So you can use a linear fit, which means it's a straight line. You can use a spherical fit, which means it'll look like a shape that increases and then levels off. You could use an exponential fit, which means it goes up like that and something interesting happens. Or you could use a Gaussian fit, which looks like a normal distribution. So any one of these models can be used to fit, and then you will study what is your nugget, what is your sill, what is your range. And this will give you an idea of the models that you want to pick at. Basically, it's also giving you the R squared, which is the value in this column right here. It is also giving you the residuals right here. And you can see, you can easily pick a model that has the highest R squared, which in this case is the linear model. And in many cases, most people will prefer, even an exponential model. So you could sort of pick the one based on the R squared values, or you could pick a model looking at the least amount of, any one of these in terms of values. You would want to have something that has the least amount of nugget. But the least amount of nugget here, which is 0.15, did not produce good R squared. So if you want to stick with the R squared, you could go with this because all of this is given to you. And in general, most people in statistics would prefer the R squared values. And this is the residual sum of squares. I was just thinking. So you'd want to look at the one that is the largest. So let's take a look at the ArcGIS exercise I have for you. I don't know what time it is. Okay.
Enough time, Prof. Suchi.
I have time.
Enough time. Yes.
Okay, so I'm going to go into my ArcGIS window and show you what I have. And meanwhile, I have to stop sharing this screen and go to a different screen. So let me go to my shared screen. So this is my ArcGIS map that is on a different computer, which has got ArcGIS. So I want to tell you what's happening here. This is an example that comes very close to the Indonesian example. So this is the sea coast along the eastern seaboard of the United States, right here. This is the most important fishing area in in our state. So if you look at the map, it shows you where it is in the eastern seacoast. This is called Portsmouth and Cape Ann. Portsmouth to Cape Ann is in the state of New Hampshire. These are all very important fishing areas. And so obviously, I cannot go far into the ocean in order to get my data points. I collected sediments and samples at this sort of location. So I'm going to obviously look at this map and show you a few details.
Many computer, eh?
So that's what the map looks like. If you look at the points, I am measuring at every one of those red points. Sorry. Yeah.
Yes, excuse me, share screen, Prof. Suchi.
Oh, I'm not sharing the screen. Sorry. Sorry.
Yeah,
I'm
it's
like,
okay because
what is happening?
Because I see from here there are many computer in your room.
Yes, that is true. Now I have to look at sharing screen. Sorry, I did not mean to do that. I think I have like 3 or 4 computers in this room. So I'm doing all my GIS work on another computer. So this is the computer screen that I wanted to show you. Okay. Can you see my screen now?
Yes, clear, Prof.
So this part of the coast of Massachusetts is the coast which is north of Massachusetts, north of Boston, in the state of New Hampshire. So I have data points from the ocean. This side, which is all the red data points, and the blue is the ocean. It's the Atlantic Ocean. I collected, and this was a data set that was shared with us, that was collected by the USGS. They collected many different data points, and they looked at the size of the grain of the sand. Because remember, I told you my interest is to look on coastal sea erosion. And I want to bring sand from the ocean and put it on the beach that has no sand. So I'm doing what is called beach nourishment project. So I want to look at all of these samples to look at the sand, and I want to create a creek surface of the depth of the sand. So that is the information I'm looking at. So first of all, I am given, and then for certain areas of the map, I have both the bathymetric values, which is this particular thing, the bathymetric values of the ocean, which tells me the depth of the ocean. You see, very near the coast, the ocean is not very deep. But if I go 100 miles out, it is dark in color because it's getting very deep. Usually, I cannot even go into that kind of depth and get samples. It's pretty expensive to get samples so far away from the coast. But now things have changed, and I know we are doing something different. But I wanted to show you, those are the layers of map I have. I also have, side scan radar and map from all other kinds of instruments, But I'm looking for the kriging exercise. I want to look at my field observation. So I went in and dropped the instruments in a buoy and dropped it in the ocean. And I got a reading. And that's where I get the red points for which I have data. So I want to use the red points, create a Krieg surface, and I want to compare it with the side scan sonar radar data. Under the ocean, I can send a scanner, and they drag it to the ship, and you can get in all kinds of information. But it is very expensive because I have to run the ship in so many different directions, like draw number 8 to find out, what's happening in terms of how many photos can I take with the scanner. Professor Helmi, do I make sense? This is very expensive to run a sonar scanner on the ocean surface. So we do have some scanners that go in all directions in the ocean, and we collect information about the fish, about the corals, about the sand, little fish called sand lands. We are doing a lot of data collection in the ocean. But I thought I just need to focus on the points. So when you get into GIS and you see these points, and I have the data coming in terms of bottom samples, I can look at the bottom sample data and open my table. And the table should show you, and I can share this data with you. The table shows you northing and easting, the latitude and the longitude, and it is showing you the mean of the millimeter size of the sand that was measured at that location. I'm measuring the size of a sand particle at every location, and it's a mean size, meaning I took a bag of sand and I'm creating a distribution and calculating the mean of the distribution. Questions? So that's my table value here. So I want to make use of this data. And obviously in GIS, you can say you want to go display the data in X and Y, and it'll ask you what you want to use, what's your X field, what's your Y field. You go give it the values. You say that you have mean things as your Z value and say, okay. And it is going to bring in those values as sample events. And you can go in and, you know what to do next. You can go and save it as a layer file or as a shape file and put it back into the distribution. So if I were to remove all this, this is my layer file map that I made. This is a shape file map that I made. So now I can look at the attribute values of that shape file. So the shape file map is very important because that is what I'm going to use for my kriging exercise. Are you all with me? All I did was I took my point data, which had X coordinate, Y coordinate, and it had Z. The Z here is the size of the sand, mean size of the sand. And I have it for a certain number of locations in this area of Cape Ann. I want to use that data and create a Krieg surface because I don't know about ocean particles because the ocean is huge. So I want to create a kriging surface. So I want to go in and take a look. And If you want to open kriging, you have to go in and say you want to customize the tools. It will give you the toolbar, and in the toolbar, you would select the geostatistical analyst. The geostatistical analyst in ArcGIS is the one that has the kriging package. So I'm choosing that. And the minute I choose it out of this window, it is going to give me the kriging on this side. It actually opens this up. Can you see this little icon there, right here?
Yes.
So now
Yes.
I'm ready to run with it. I can go in and press that, and it says, do you want to explore your data? Let's say I want to create a histogram. It knows that it can create a histogram of the value of the data set, and hopefully it's predicting the right one. Oh no, it's doing the site ID. Okay, hang on a second. So in the field point observation, I want the mean millimeter depth, not the site ID. So that's the distribution. There is a lot of sand particles which have tiny sizes because it says that it's 0.1 to 0.2 size. And there's very few sand particles, samples, that are above a size of 1.59. Look at this. Very few samples right here. More samples over here. So this histogram enables me to judge what am I going to see in my kriging. I'm going to see a surface that has very small sand particles. That's the sampling that I have done because I'm doing near shore sampling. So I could go in and I could also go into the geostatistics and I can do a few more smart things. I can do the normalized QQ plots. That should give me an indication of what type of kriging I can use because it tells me about the fit of the data. The third option is Voronoi map. I can take all of the points and create a surface, which is called a Voronoi tessellation. And I'm sure you've done this in GIS. Take a point data and create a surface. I can also create a trend analysis to find out what does it look like in terms of the values of these points over space. I can also look at a semi-variogram and covariance cloud, and I can also do, several other things, general QQ plot. I don't normally try all that. The next one I want to show you is the normal QQ plot. Again, I want to go in and look at my mean value. So the normal QQ plot tells me that in general, the values are fitting very well with my linear fit. But somewhere up above in this area, I have a lot of outliers. See, it is giving me an indication that certain parts of the map, it's above the normal prediction. So there's something that is sort of going on. I can also transform all these values into log values. So I get a different plot with the log values than using regular values. A log value is very useful if you have wide ranges in your distribution. You need to take a log scale. So I'm looking at a log scale and saying, hey, it's not too bad. There are some values that are deviating away in a QQ plot, but I'm able to make sense of it. I could do that. And all of these maps can be added to your layout, and you can make a very nice, visualization. So proceeding further, I want to draw a Voronoi map. So if I were to draw a Voronoi map, and again, make sure that you're choosing the right thing. I want to do the mean particles. And I generally like to give nice bright colors. That's what it looks like. There is a lot of particles which are kind of on the heavier side of size that are closer towards my coast, towards Cape Ann. And Further away from the coast, the particle size is tiny. So heavier particles, bigger size particles are closer towards the coast. I think they didn't have a chance to break down and become smaller because of coastal wave erosion action. Waves constantly are pounding and the sand particles become smaller and smaller. And so they have to be further away from the coast where there is a lot more wave action. So that's what this Voronoi tessellation is showing me. So this is a simple type of a map. Obviously, I can look at many different maps of Voronoi tessellation. I also very much like this thing called entropy. And entropy for me is based on physics. So you should read about this, map which is based on entropy. I don't have time to go into it, but please look at it, look at it and try to understand. But if you sort of have any sort of issues with it, use the simplest model. If you want to be a little more adventurous, use the mean. If you want to be statistically correct, use the standard deviation. Those are your choices. Looking at things like entropy and things like that require a lot more knowledge. So I would go with simplicity. So are you guys with me? Can I proceed? Okay. So once I have done all this, I add all these maps, right? I can see all these maps. So now I want to, the ocean is very, very interesting in certain parts. So now I want to get into looking at the map in terms of a few more, details. So if I go back to the geostatistical analyst and I were to use the wizard, geostatistical wizard, this particular wizard will walk you through all of the methods. At the top, it gives you deterministic methods, which is inverse distance weighting method. Everything is highly predictable, and the inverse distance weighting method is the simplest one. People have started using other things under the deterministic methods, including radial basis function. But I don't have time to go into it. If you are interested, you should read it. So let's say I want to go into the inverse distance weighted method. I can press that and it says, what is the data field that you want to use in this file called field point? Obviously, I want to use the mean millimeter depth. And then it's asking me, do I have a weight field? You can say, if you have any ideas on the weight field, you could add that. But obviously, we are all concerned about the mean, size of the sand and not any other variable. Sometimes you may have the depth of the ocean, as a parameter that you want to look at. In this particular case, I don't have the depth, but obviously depth is a very good weighting scheme in the ocean because depth represents like height on the mountain. I don't have it, so I can either go with this or leave it blank, right? So when I go in terms of the geostatistics, it actually draws for me and says, here is the area of inverse distance weighting. And, if you want to see more, it will give you all the notes here and it will tell you what it is in terms of what is it that it is giving you. If you go to the next map, it will kind of show you the plots. It is giving you what is the predicted value and what is the measured value. The measured minus the predicted value is the error term right here. The predicted minus the measured is the error term right here. And you can make a plot of it using this kind of, fit. And you can see your blue line of plot is going here. This is the fit, not this line. There is a lot of, but there are a couple of points up north which are outliers. And it is giving me all of this, and it's also giving me the root mean square error, which should give you a very good indication of the model fit. And that's the root mean square error. And it is also giving me the regression equation here. And I can look at the errors. The errors seem to beautifully line up. There's some relationship to the errors that it shows. So those are the things that I got out of the inverse distance weighting method. I could save that, or I can get out and cancel it. So let's say I want to go to the next plot in terms of the geostatistical wizard. And now I want to get into the actual kriging methods. So I can go into kriging. So it's asking me what's the source data. Obviously, it's the mean millimeter depth of the measurement of the sand. Then it's asking me, do you have a second data set, third data set, and so on? I don't. I only have one little data set. And then it is asking me, do you want to use ordinary kriging, simple kriging, universal kriging, indicator kriging, and you should read this, probability kriging and disjunctive kriging. I have never used anything beyond in terms of these two. I've only used these simple measures on the top. And I always prefer either the universal, simple, or ordinary. I haven't been very adventurous because I don't have good enough data to do this. So maybe when I work with Professor Helmi, I may get some real measurements that we can use for the beaches of North Bali and run a geostatistical, analysis with it. The student should do it as an exercise. It might be good. So then I can also look at what is the output surface do I want? Do I want a probability in terms of where is the best things I'm doing? Do I want an error map? Do I want a prediction? Or do I want a quantile? So let's go with prediction. And I've chosen the very simple, I can choose ordinary. I can choose the ordinary type. And then it's asking you, do you want to remove the trends? And you can say, I want to remove a first order trend, second order. So this all gets to be, higher level of statistics than what we are learning. So do you want to use the regular value, or do I want to use a log value? Or do I want to use an arc sine value? I just keep it simple. And I can say next. So now it's going to produce for you the surface and the prediction. And it is showing you the average distance, the model values, the predicted bin values, and everything else. And it is also giving you all kinds of things in terms of, value. You can ask what's the value of the lag, number of lags. You can set anything you want. All of these can be optimized for your application. So when you finish up, it makes such a map. It tells you what's going on. It's used the maximum neighbor size of 5 points, a minimum size of 2 points in order to make the map. And it is obviously giving you the predicted values of X and Y at this location that, it's predicting for. Because this is the area of the point at which there was no values. So the program automatically thinks that it should go select an area or a point at which you have no observation. So it is automatically choosing that because we've gone through the wizard and it's telling me it would choose that. Here is what it gives in terms of predicted value, errors, and so on. It's also giving me a regression equation. It's giving me all the error values, standardized errors, normal QQ plots. That's not a bad fit. It looks okay. And the predicted value, I can look at this equation and it tells me what's happening in terms of the regression equation. And I have the root mean square error to be 0.4. I have the average standard error. So all of these terms I can compare between the many different methods, and I can finish up getting the values of all of this. Since I asked it for a predicted value, it went through just the prediction. I could have asked it to make a prediction of, I could have just asked it to make a prediction of sill range and, a sill range and nugget, and it would have given me those values. So let's take a look at it before I finish up. So I'm going into kriging. Oh, more recently, the idea is empirical Bayesian kriging has become a very popular method. A lot of people are also, looking into more complex examples of kernel smoothing and other techniques. But to begin with, you should do something very simple. So that's what I would stick with. So again, I want to go in and say, look at the mean things. And I wanted to look at the source data. I'm using, let's go with ordinary kriging. I can try any of the models. So I can say that I want prediction, probability, predictive standard error. Let's go with probabilities. So now it's giving me, giving me the ideas of if I were to do this, and this is the value that it wants to predict at, right? So the predicted value at that X and Y coordinate, it's going to show you all of the things of what its prediction is. And it is giving you how it sort of used the semi-variogram, and it gives you the model values and so on. And, I could have set anisotropy to be true, which means it gives me the directional values. It's giving me the range, and it's giving me the partial sill value, which is this. And it's able to produce all these values for what I achieved there. So here is the map that looks no different from the previous map. And it says that 45-degree offsets it's taken, and it's given all of the values around. And I can see that this produces a different plot. So the way I would go about choosing between the different models is to go in and run all the values, look at the measured value, the errors, look at all of the statistics in terms of the nugget, range, and sill, and do a very nice calculation with it. And I would choose the models based on comparing all these different methods. And I think I'm going to stop here. So to take questions and have more of an interaction.
Okay, thank you very much, Prof. Suchi. I learned many things this morning.
Yeah.
And I think also the student and all of the participants that joined on this valuable workshop this morning. Okay, let's see the participant question. I think there is no question in chat. If you have any question, you can raise hand and you can doing directly question. You can provide in Bahasa Indonesia and I can help you to translate. That is okay also.
I can also share with you an ArcGIS manual for geostatistics.
Right.
The document.
Right. That is
and
very
I can
important.
also give you the data set.
Yes.
Not this Massachusetts data set, which is like a real data set. ArcGIS gives us a California ozone data. So people can work through the example.
Okay.
So I will give you the manual and the data set. So students should try it out. That's the exercise you have from me.
Yes. Thank you, Prof. Suchi.
Yeah. So let me do that before I forget.
Yes. You can send it to me, Prof. Suchi, and I will share to the committee.
Yeah, sure.
Silakan Bapak dan Ibu, teman-teman mahasiswa. Kalau ada pertanyaan silakan disampaikan, bisa bahasa Indonesia, nanti saya bantu translate bahasa Inggris. Jangan ragu dan takut. Kalau ada yang mau chat juga boleh. Kalau ada dari YouTube juga silakan Mas Ayas untuk bisa disampaikan. Jadi beliau akan memberikan juga modul dan data untuk kita bisa gunakan untuk latihan. Silakan saya tunggu.
Any questions?
Okay, we have from chat, Prof. Suci.
Mm-hmm.
Yes, this is very good question. I think from Muhammad Jazman. Yeah. Is there any general rule of thumb on how many sample need to took per square miles or per kilometer to predict kriging with lower RMS error? This is good question, Prof.
Yeah,
Suci.
yeah, very good question. If you can, you should collect as many samples as possible. If you can't do that, you need to have enough number of samples to describe the spatial heterogeneity. Like in Bali, North Bali that we are working on, you cannot just get points right off the coast. You also need to get points deep in the ocean. So, there is no way to sort of describe it. The more points you have, the better is the prediction. If you miss out some critical points, you're going to make big mistakes. So if I'm mapping the Himalayas and I miss Mount Everest or Mount K2 as my points, imagine the whole height of the Himalayas would come down. So we need to obviously make sure we have all the critical points and we have a good enough spread. But if you don't have it, then you're going to go with what you have. Hopefully it is spread all over the region that you're interested in. And it is not just capturing one set than the other. So in my ocean example, I've given you points all across. Even in the deep ocean, I've given you points. But there are more number of points in shallow depths than in the deep ocean. See this? Fewer points in the deep ocean because it's more expensive to collect points. But I made it spread north to south, east to west, so I have enough points. So there is no magic rule. You need to have a good intuition. You need to have a good scientific understanding of what are you going to do with this? What should the prediction be, right? And how spread out should the points be? You cannot oversample one area and undersample another area. Because remember, you're describing spatial heterogeneity, which means it's a pattern. And if you want to do any statistical things, you at least need 30 points for a small area. Like the beaches of North Bali, I need 30 points. For the ocean here, I think I have more than 100 points. For the California ozone data set, it is dependent on the number of stations that collect information on ozone. Those in the United States are many. In Indonesia, if I'm measuring air pollution, in India, I don't get any. India has huge air pollution problems. Can't get a measurement. So I will never use kriging in India. I have 2 data points. for all of the city of Delhi. How can I make a creek map?
Okay, thank you, Prof. Suchi. Very clear explanation. Is there any question? I mean, direct question is recommend, please. We still have around 4 minutes more, Prof. Suchi.
Yeah.
Yes.
So I want all the students to use the workbook of ArcGIS that I'm going to give you and use that sample data set in California, because it's explained very well in the book. And they should complete the exercise if they are interested. Can you please share it with everybody, including all the 400 people from all islands?
Yes, yes. The committee will do that, Prof. Suchi.
Yeah. So
Because,
it is very good for you to do this. And obviously, if you want this data, I can give you this data. But I find the California data set is very nicely explained. Every technique of kriging is explained. Kriging is a whole semester course.
Oh, okay.
It is not one lecture. In my classes, I lecture twice. And my students, I have been with them all through, and it's all technical. And they know it because they know spatial autocorrelation, they know distance weighting, they know rooks move, queens move, they know everything before we come here. I just finished this. I finished geostatistics, and I also did geographically weighted regression. And by the way, you really don't need ArcGIS. The program called R has all the geostatistics. So for my more advanced class, I ask them to program. I don't give them ArcGIS, no way. They have to work in R because I want them to program.
Okay. Okay, thank you very much, Prof. Suchi. I think we still have around 2 minutes, not enough time again to question and answer. Okay, as moderator and as the name of our university, Diponegoro University, and as the name of Faculty of Fisheries and Marine Science, and also as the name of the committee, ReGISFest or Register, I would like to say thank you very much, Prof. Suchi, for excellent presentation and also very complete module that you provide. So very good presentation and good demonstration in the short time, and also the very good module, I think, and also provided with the data. I think from that complete information and material that you have provided on this short workshop, and hopefully our student especially, and also our government officer can, and also researcher here in almost of the representative of almost of the Indonesia province join in this meeting will have beneficial to understand more about the geostatistic information that is rare information in Indonesia. Yeah. Again, Prof. Suchi, thank you very much. And as a moderator, I would like to apologize if I have some mistake on this time. Yeah. And again, Prof. Suchi, thank you very much for your time. I know that you are very, very busy with the very tight schedule every day. Yeah. Thank you very much again, Prof. Suchi. And I give the time back to the Master of Ceremony. Thank you very much and good morning. Yeah.
Yeah, thank you. Thank you all.
Okay.
Thank you all students. Yeah.
Okay. Bye, Prof. Suchi.
Bye.
Okay. Silakan Mbak Rahmadiani.
Terima kasih kepada Dr. Muhammad Helmi, S.Si, M.Si selaku moderator, dan Profesor Sucharita Gopal, PhD, atas materi yang telah disampaikan. Selanjutnya akan diadakan sesi foto bersama. Untuk para peserta diharapkan menyalakan kameranya. Kepada PJ foto saya persilakan.
Izin mau foto 1, 2, 3. Enggak. Lagi 1, 2. Ya, terima kasih. Saya kembalikan ke MC.
Baik, terima kasih. Acara selanjutnya yaitu isoma. Kepada para peserta dipersilakan untuk beristirahat dan melakukan aktivitasnya. Diharapkan kepada peserta masuk ke dalam Zoom meeting kembali pada pukul 12.50 karena acara akan dimulai kembali dengan pemaparan materi kedua. Terima kasih.
Terima kasih. Sukses ya Mbak. Lancar untuk hari pertama. Izin pamit nggih.
Baik Pak, terima kasih banyak.
Terima kasih banyak.
Kita semua ya panitia. Terima kasih juga untuk semua peserta yang hadir. Pertanyaannya bagus-bagus. Terima kasih nggih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Assalamualaikum warahmatullahi wabarakatuh.